When we talk about kinematics of circular motion, we're going to be talking about things that move in a circular path. Okay, not yet things that are spinning or rotating, but just things that move pretty simply in a circular type path or orbit. Okay. So before we can get there, I want to talk a little bit about the overall path of this. Okay, so if I have an object that's moving in a straight line, what has to have happened for that object to be moving in a straight line? Yes, something has to make it move. What's that called? Force. A force. Good. So if I have an object moving in a straight line, that means my net force is in the same direction as my motion. Okay, most of the time. Right, I've got some applied force that's making that object move in that direction. Okay, so my net force has to be in that direction to get it to move in a straight line. What causes something to move in a projectile path? Okay, and what's a projectile path look like? Yeah, good. Up and then back down, right? It's moving horizontally and vertically. So what has to happen for an object to move in that type of a path?
Has to be launched or thrown. Yeah,
launched or thrown. It's got to be at that initial angle. Very good. Okay, so our net force has to be at an angle this time in the direction of our motion. Okay, so if I want straight line velocity, I can apply a net force in that straight line. If I want a projectile type path, I have to have my net force be at that initial angle. I want my projectile launched. So circular motion, is it more similar to a straight line path or a projectile path? Which does it resemble more? Projectile, good. Okay, so objects moving in a circle have similar qualities to projectile motion. The good thing is that solving circular motion is much simpler than projectiles. We don't have to break things down into X and into Y. Okay, so circular motion is a little bit more simplistic, although it follows some of the same guidelines. Okay, so we're going to talk about uniform circular motion. What does it mean for an object to be uniform or a system to be uniform? The same, good, means the same. Okay, so in other words, that means constant. So constant circular motion. So when we are looking at this circular motion, we're looking at pretty simplistic versions. And we're looking at objects that move at constant speed in a circular path. Okay, so constant velocity. We're not looking at things that speed up or slow down while they are moving. Okay, so we said our objects move at constant speed, but what's the difference between speed and velocity? That's right, that's right. So velocity has to have two things, and what are those two things? Magnitude and direction. So all vectors have to have magnitude and direction. So there's our difference between speed and velocity, right? We said it moves at constant speed, but we didn't say it moves at constant velocity, and there's a difference there. Okay, so as something's moving through its circular path, it's going to be changing directions. Okay, so if I have an object in a circle like this, okay, that thing is moving at constant speed. It's not speeding up or slowing down, but it's constantly moving directions. Does that make sense? So we have a change in velocity, even though we don't have a change in speed. Okay, does that part make sense? Okay. So magnitude of velocity remains constant, but direction is continuously changing. Okay, you can abbreviate that down or just, kind of make that a little shorter than my bullet point there. But essentially what I want you to understand is that speed might remain constant, but the velocity is continuously changing. Okay, so if we have a continuous change in velocity, that's otherwise known as acceleration. Okay, it is a change in velocity. What do we normally think of acceleration as, though? Good, speeding up or slowing down, right? Deceleration. But that's not always the case, right? We could be traveling at the same velocity but going around a corner, which would technically be called an acceleration because it is a change in our velocity. That concept is going to be a little tricky to wrap your mind around because we're so used to acceleration being the magnitude of velocity changing. Okay, so since velocity is changing by direction, an object revolving in a circle is constantly accelerating even though the speed remains constant. Okay, so things that move in a circular path do have a constant acceleration. Okay, they are continuously changing continuously changing velocity because their direction is continuously changing. Okay, centripetal acceleration. So this is a good one for your equation sheet. Okay, this is still chapter 6, so it can go on there as well. So acceleration, this little subscript C just means for centripetal acceleration is equal to velocity squared over r. What might we associate r with? The radius, good. And what unit do you think that should be in? Centimeters, meters, kilometers? Meters, good. Radius should always be in meters. So you might want to put that in there. When we look at centripetal accelerations, the word centripetal means center seeking. Okay, so an object moves in a circle with a radius r at speed v. It has an acceleration whose direction is toward the center of the circle. So this is a little bit hard for us to imagine. As it's accelerating, we see a couple vectors here. Okay, so here's my circular path. Here's my object and its velocity. The acceleration is always perpendicular to that velocity. Okay, and this is more than we really need to get into, but this is the case for centripetal acceleration, is that acceleration is constantly toward the center. Okay, it has to do with Newton's third law and the forces that are going with that. But you always need to pay attention to the fact that acceleration is going to be pointing toward the center of the circle. Okay, when we work with circular motion, something else that we should notice is that the center of the circle is always the positive direction, no matter what. Okay, so that's something else that's a little bit of a change for us, is that the center of the circle is always the positive direction. Okay, since these things are center seeking, it makes it simpler for us to just assume the center of the circle is the positive direction, and then outward from the circle would be the negative direction. Okay. Okay, as we see our radius of our circle increase and decrease, so let's see if I start out at this radius, right? My acceleration or my change in velocity is pretty constant, right? It's moving at the same speed, which means it's changing direction at the same rate. Okay, if I decrease the radius, but I spin at the same rate, is my direction changing faster or slower? My direction is changing faster or slower. I decrease my radius, or the denominator of that problem, which means my answer should get bigger, right? My acceleration increases. As I increase the radius and I spin at the same speed, okay, I'm changing direction at a much slower rate. Okay? I'm not covering as much of the circle per time as I would be the smaller the radius is. So as you get a really small radius, it looks like it's spinning a lot faster, right? Even though I'm not moving my wrist any faster than I was at a longer radius. Okay? So I can keep my wrist constant, but as that radius gets bigger and bigger, it covers less of the circle, right? All right. So we're going to start talking about something called period and frequency. Frequency first. So I'll give you what this equation means here in just a second, so don't worry about that for right now. Frequency is described in terms of how many revolutions are made per second. Okay. So what is a revolution, first of all? That's right, one time around the circle is a revolution. Okay, it could also be called a rotation. Okay, but one revolution is one complete trip around the circle. So frequency we describe as revolutions per second. Okay, so how many revolutions did it go through in 1 second? Sometimes it might be a fraction, right? If it doesn't make it all the way around in 1 second. Sometimes it could be 16 revolutions per second. Just depends on the rate at which it is spinning. Okay? So revolutions per second is frequency. And frequency is a lowercase f. Okay? Its units are either revolutions per second, or sometimes you'll see them as hertz. HZ. Really sorry, capital H. Okay? Most of the time in this chapter we'll see them as revolutions per second, or revolutions per minute, or whatever you want it to be, but it's usually revolutions per time. Okay? Period, on the other hand, is the time required to complete one revolution. Okay, so frequency is revolutions per second. Period is time per revolution. So they are reciprocals of one another. So period is a capital T. Make that, that should make you think of time. Okay, capital T is time to make one revolution. Okay, and usually we want period to be in seconds. Okay, in order for period to be in seconds, what does revolutions have to be in? I'm sorry, what does frequency have to be in? Revolutions per second. Revolutions per second. Okay, so we want those to match. We can connect period and frequency using this bottom equation. T equals 1 over F, or you could do it the other way around and say F equals 1 over T. Right, when we want to solve for the bottom variable, we could just switch those two. So this is the main equation for period and frequency. This one would also work. So if I was using my little device over here, and I was spinning that, and I knew it made 3 revolutions in 1 second, is that period or frequency? If I knew it made 3 revolutions in 1 second. Good. My frequency would be 3 revolutions per second. So what would my period be? 1 second? 1/3, right? 1/3 of a second. Okay? So if it makes 3 revolutions in 1 second, you should know that each revolution takes 1/3 of a second. Okay? And I don't like fractions, so you would really convert that to 0.33. Okay. I hate fractions. Okay. Anyway, that's how period and frequency work. You will get mixed up on the units that go with that. So please be careful. Right? Time or period should always have seconds as the unit. The other one might say revolutions per. Okay? All right. Okay. What is this? Oh, I already gave it to you. This equation should be familiar to you. This top one, what is it? Circumference of a circle. Why do you think we might need to know the circumference of a circle? Why would we need to know that equation? That's right. That's right. If we're talking about circular motion, we want to see the distance that object has traveled. We're going to need to know the circumference of the circle. So, if I take distance it travels over the time it takes to travel that one circle, what does distance over time equal? Velocity. Okay, so for objects at constant speed, we can combine period and velocity into one equation, period and distance and velocity into one equation. So this is one that you would probably want on your equation sheet. Okay, velocity equals 2 pi r over t. Okay, and then this bottom little bullet just kind of explains why that works again. 1 revolution is 1 complete trip around a circle. That means it's traveling the circumference. And the period, or the capital T, is the time it takes to make 1 revolution. So we travel 1 distance around the circle. We have the time it takes to do that. That gives us the velocity. Okay? And what would our units for velocity be here? Meters per second, right? 2 doesn't have a unit. Pi doesn't have a unit. Radius units should be meter. Time units should be seconds. Okay, so we still want our velocity in meters per second, just like normal. Our equations for acceleration and velocity now into one larger equation. Okay? And let me just show you how this works. You don't write anything down yet. I'll just kind of show you how we're going here. Okay? Our centripetal acceleration equals velocity squared over r. We already saw that equation. All that I'm doing here is substituting velocity, which equals 2 pi r over t. I'm substituting that in this equation. Okay, but v is squared, so we have to take 2 pi r squared over t squared. Okay, do we see where that substitution's been made? We good with that part? All that we're doing down here is expanding that equation out. Okay? This equation you can choose to write down on your equation sheet. Okay, that's fine, this expanded one. But realistically, what you could do is if you're given radius and period instead of velocity, you could always just solve for velocity first and then plug it into that v squared equation. Does that make sense? Okay, you don't have to use this big, like jumbo equation here, but you are welcome to. Okay. Questions? Okay. Very good. Okay, now we're using the forces that put these objects into that circular motion. Okay, so chapter 6 talks about the kinematics that go into circular motion as well as the dynamics, okay, or the forces that go into centripetal motion or circular motion. Okay, F net equals mass times acceleration. That is Newton's second law, right? The net force is equal to the mass times the acceleration of a system. All we're doing here is we're taking the forces of that circle, or the centripetal force. You might see it written like this. Fc equals m times ac, right? Because the net force here is the same as the centripetal force. Mass times centripetal force. All we're doing here is expanding that by substituting v squared over r for acceleration. Okay, so either one of these equations or both can go on your equation sheet. Okay, Fc is centripetal force, the same thing as net force here. Okay, so you'll see me probably write that both ways. 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making 1 revolution in 1.8 seconds. Find the tension force by the string on the stopper. Go ahead and get written down what you need to. When it says it's swung in a horizontal circle, that means it's like something like this. Okay. The length of the string, do we need to divide that by 2 for the radius? What do you think? No, right? If I'm acting like this is all 0.93 meters, the radius itself is the length of the string, right? Because that's the distance from my object to my center axis. So that whole length of the string is going to be our distance. You don't have to divide that by 2. Okay, so let's say this is kind of a bird's eye view of my motion here. Here's my stopper. And it says I want to find the tension force exerted by the string. So I've got some tension force. Okay? That tension force is toward the center of the circle, right? Because that's where the string is going, toward the center of the circle. And where did we say the positive direction was? The center of the circle. So that's our only force there. Okay? So our tension force is really just equal to our centripetal force. Okay? The same as our net force. I know I'm throwing a lot of names of forces out at you, okay? But our net force is our overall, which in this chapter is the same as our centripetal force. Okay? So here our tension force would be equal to our centripetal. Does that part make sense? If there was something opposing that or going opposite of tension, we would have to say tension minus something equals a centripetal force. In this case, there's no such opposing force. Okay? On the same page there? Okay. So let's look at what else we have here. Our mass is 13 grams. Is that what we'd like it to be in? Do we usually want mass in grams? No. What do we want mass in? Kilograms. We want mass in kilograms. Okay? Always, always in kilograms. So to go from grams to kilograms, we should divide by 1,000. Okay, because kilograms should be a small number there. So 0.013 kilograms. Okay. Our radius here is what? 0.93. Good. Do not divide that by 2. A lot of people think that, that's the diameter or something. Okay, and then it tells us it makes 1 revolution in 1.8 seconds. Is that period or frequency? Period. Good. T equals 1.18. Picking that out, period or frequency, will be a stumbling block for a lot of you. So make sure you pay attention to the units. Okay? It's 1 revolution in this many seconds. So that has to be period. Okay? So now let's start looking at our equations. If we're solving for tension force or centripetal force, we could say centripetal force is equal to mass times acceleration. Okay, do we have A here? Do we have acceleration yet? No. Okay, so that's not going to work. We could try this one. mv. No. V squared over r. Do we have velocity yet? No, that's not going to work. And how do we solve for velocity then? What's our equation for velocity? 2 pi r over t. Do we have those things? Yes. So let's do that first. Let's go ahead and solve for velocity, then we can plug it in there. Okay, so velocity equals 2 times... You can use the pi button. You can use 3.14. It's going to make a tiny bit of difference in the rounding. It's not a huge deal. I usually use the pi button. Okay, so our velocity. Sydney, what'd you have? 4.95. Perfect. Okay. And from there, where do we go? That's right, we want to plug in velocity over here. Okay, so let me get rid of this. We say centripetal force is equal to m times v squared over r. So 0.013 times 4.95 squared over 0.93. You're just squaring the numerator here. Okay, so on this problem, they gave you everything you needed, right? Do you have to solve for anything first? No. All we wanted was acceleration. So we're going to take acceleration equals v squared over r. That was it. Oops. 8.8 squared over 25. Robbie, what'd you have?
3.1 meters per second squared.
3.1 meters per second squared. Good, pretty easy, right? Okay, so they can be pretty simple like that. They can be a little more complex. That's going to take you some conversions, take you some calculations first. Okay, so horizontal is pretty straightforward like that. Any questions about horizontal circular motion? Okay, let's look at vertical now. All right, a 0.150 kilogram ball at the end of a 1.1 meter long cord. Is swung in a vertical circle. Determine the minimum speed the ball must have at the top of its arc so that it continues to move in a circle. Okay, and we made the note to make toward the center of the circle the positive direction. Okay, so as we're looking at this vertical circle, we want to find the minimum speed the ball must have so that it continues to move in a circle. Continues to move, okay? So as we are twirling this thing in a vertical circle, what happens if I get moving too slow? What happens to my circular path? Yeah, it falls out of its circular path, right? If I swing this faster and faster and faster, we'll see the tension increase. We'll see a much greater probability of it staying in its circular path, right? As I slow this thing down, right, you'll see it kind of start to fall out of its circle. We want to find out what's the very slowest that it can travel so that it doesn't begin to fall. That it's just going to be just enough to keep it in its circular path here. Essentially, we have no tension in this string because it's just hanging there. Okay, it's not pulling out, it's just going to be hanging. Okay, so we're just enough to keep it there. All right, so with that being said, I went ahead and drew my free body diagram here. And we've got a tension force that's toward the center of the circle. What else would be pointing downward like that? Gravity, good. Okay, but we said this is the positive direction. So as we start to look at our net force or our centripetal force, right? I'd set up my equation. This is just like F net. Okay, so I want positive forces minus negative. These are both going in the positive direction. So what should I do to them? Add them together, that's right. So I would say the tension force plus the gravitational force. Okay, and I'm adding those two together because when it's at the top of its path, those are both pointing toward the center direction, toward the center of the circle. Okay, the positive direction. But I said that I want just the minimum speed, so I have no tension in my string at all, right? I want it to see how slow it can go, and so it kind of gets to start getting a little bit loose but doesn't fall out. Okay, so that means my tension here would be 0. Okay, this is only the case when we're looking for the minimum, right? If I was just looking for the regular speed at the top of its path, if it was going certain, whatever, our tension would not be 0. But in this case, we want to find the minimum. So what's the very least we can do to keep it in that path? Okay, how do we find FG? How do we find FG? Good, mass times gravity, so 0.150 times 9.8. And that's equal to the centripetal force. Okay, let's go ahead and solve that part first, and we'll go with centripetal force. That's all that's holding it in that circular path, yeah. Okay, that's just the centripetal force. That's not the velocity. Okay, so now let's look at how we would solve for velocity. What equation do we have that we can set up there? Fc is equal to what? M times v squared over r. Okay, so we have centripetal force. We would say 1.47 equals mass times v squared over r, which is 1.1. Okay, so algebraically, you can do this in any order you want, right? I'm going to get rid of that denominator, so I'll multiply this by 1.1. So I can cancel that on this side and multiply this by 1.1. And then divide by that 1.50 to get it to the other side. Right, algebraically, you can do that in whatever order you want. And then once you do that, you're going to have to get v by itself. And how would you go about doing that? Square root it. Good. Okay, so this time we're looking at the bottom of our arc, of our circular path. So here's the bottom of it. And here's our object this time. Are tension and gravity going to be pointing in the same direction here or opposite directions? Opposite directions, good. Tension still goes toward the center of the circle, and gravity still always points down. That's exactly right. Yep. So when we set up our net force or our centripetal force equation, we would take tension minus gravity. Okay, so this centripetal force is acting just like our net force here. Tension is going in the positive direction because it's going toward the center of the circle, which is positive. And gravity is always downward, which is away from the center of the circle, so it's negative. Okay. This time we want to find the tension. So our tension is not 0. Right? We want to find that. So we're going to solve for Ft. Fg, we calculated that last time. It's the same ball on the end of it. So our gravitational force should again be 1.47. But this time we're going to be able to solve for our centripetal force, right? Because we know our velocity, we know our mass, and we know our radius. Okay, are we all feeling okay about that part? Okay, I would plug in m times v squared over r. What is our velocity in this case? It says it's twice as fast as the speed of part A, so twice as fast as the one we just solved for. So our velocity should be 6.6 squared over r. Okay, so let's go ahead and solve that. Okay, Maddie, what'd you have? 7.1? 7.41? Okay. Okay, do we agree there? All right, very good.